So last time we talked about the idea of trigonometric substitution. And in some sense you could say that one of our goals in doing trigonometric substitution is trying to help us get rid of plus or minus in the square root. Now of course it extends slightly more beyond that, but essentially that's the idea. It's like, well, I have something inside a square root. I'd really like to get rid of it. Can I use some sort of trig identity to help me do that? Now there's another place where we'd like to get rid of plus and minuses, namely if we have fractions of polynomials. So we call these rational functions. A polynomial over a polynomial. Now the plus and minuses upstairs on the top are lovely. We love those kinds of plus and minuses. The problem is the denominator. Now of course there's temptations to say, well, let me just come up with terrible rules for algebra and then life is good. And it doesn't work. You can't use terrible rules for algebra. You got to use the rules. The rules are the rules. So what we want to do is find a way, how do we handle something downstairs? Now our basic philosophy is, if you think about what's happening upstairs, you're like, oh, if I have the plus or minus, I can pull it apart into pieces. Well, today, by the end of today, we're going to see, aha, there's this lovely tool in algebra. It's called partial fractions. And it says you can do the same thing with the downstairs, but it takes a little bit of work. Now, this is an algebra technique. It's not a calculus technique. The goal here is to show how we use the algebra to make our integrals simpler so that we can actually integrate them. In particular, there's a couple types of rational functions that we enjoy. Namely, if I have something to a power, because then we have the power rule. We know how to integrate things like that. Or maybe we have something in the denominator, 1 over x minus a to the k, or 1 over x plus a to the k. We can handle those. Again, it's a power rule, or maybe it's a log, if it's like 1 over x minus a. And last time, we saw an example, how do you handle something like 1 over x minus a squared plus b squared to the k power? And the answer is you use that trig substitution. X minus a would be equal to b times tangent theta. So these are the kind of rational functions that we know how to integrate. And here's the really cool fact. It turns out that every rational function that you'll ever encounter can be written as some combination of these pieces. So what we want to do is go through the process of how do we get to that? How do we break up rational functions into these individual parts and therefore something that we can integrate? All right, so that's our goal for today. How do we do that? So the first thing you always check is you look at your degrees. So you should have a polynomial over a polynomial. And what you want to do is say, if the degree on the top is as big or bigger than the degree on the bottom, then you first need to do long division. So you want to get to the point where the degree on the top is less than the degree on the bottom. Once you're in that stage, life is good. So let's do an example. Find the integral 2x cubed minus x squared plus 4x, that's our numerator, divided by x squared plus 1, that's our denominator. So we look at the powers. What's the power on the top? 3. Power on the bottom? 2. 3 is bigger than or equal to 2. So that means we do need to do long division. So how does long division work? Well, you take what you're dividing by, x squared plus 1, and you're going to divide that into this polynomial. So you start with the highest power, and you just write it down. Now, if you ever are missing a term, so for instance, we do have a square term, we do have a linear term, that's what we call the x term. There's no constant term, so if you're missing that, you just put it as 0 as a filler. Now long division is actually very elegant. You have to answer the following question. Looking at the highest powers, what do I need? So I have x squared, I want 2x cubed. What do I need to multiply x squared by to get 2x cubed? 2x. So you put 2x. Now you're going to take this 2x and multiply it by the whole expression. So we used the highest power to figure out what we need, and now we're going to sort of update and see where we're at. So 2x times x squared is 2x cubed because we chose it that way. 2x times 1 is 2x, and I'm going to put it underneath the x term. So plus 2x. Now we're going to subtract because we've already accounted for that. So we need to take away and see what we haven't accounted for. The 2x cubes cancel by design. Then there's minus x squared. And then 4x minus 2x is plus 2x. I'll go ahead and bring the 0 down. Now we repeat the question. Look at the highest powers. I have x squared. I want minus x squared. What do I multiply x squared by to get minus x squared? Negative 1. So I'm going to put a negative 1 up here to keep track of what I multiplied by. Multiply by the whole thing. So it's going to be minus x squared. Then minus 1 times plus 1 is a minus 1. And I'm going to subtract. The minus x squared minus x squared cancel. So we're going to be left with 2x. And then 0 minus minus 1 is plus 1. Now at this point, we say, okay, now my x squared is higher power than the 2x, so I stop. So this, sometimes you might call this the remainder. So what does that mean? Well, what we have now is that our original integral, 2x cubed minus x squared plus 4x, divided by x squared plus 1, is equal to the 2x minus 1, so this is what came out, plus the remainder, 2x plus 1, divided by x squared plus 1. All right, so we've simplified our integral a little bit. And we can do one other thing. We can use the fact that we have this addition upstairs. Remember, addition upstairs is a great tool. And the reason I point it out is because if you think about our pieces, like for example, 1 over x squared plus 1, that's pretty straightforward. Can we do 2x over x squared plus 1? Do we know how to integrate that? Yes? No? Maybe? You got to go through all your old logs, your notes. But anyways, I think we can. All right. So as I mentioned, addition and subtraction upstairs is great. So I'm just going to pull it apart. Plus 1 over x squared plus 1. Okay, there we go. Now we write down our answer because, well, we don't have a lot of space left, so whatever, we better write it down our answer now. Integral of 2x, x squared. Integral of minus 1, minus x. All right, 2x over x squared plus 1. I think we're almost to the point where we might be able to do this one in our heads. Do you see what's going on? Suppose for a second you took the denominator and did a substitution. That's always something you should always think about doing. If you called this u, what would du be? 2x. So it looks like the derivative of something over the function, du over u. When you integrate that, what should you get? Natural log of u. So whenever you see a derivative of a function over a function, that's the natural log. Now, if you don't like doing it in your head, just do a substitution and you're fine. This is natural log of x squared plus 1. How about 1 over x squared plus 1? Arctangent of x. And because we want points, plus c. So there's our antiderivative. That's it. Now, I want to point out here that arctangent of x, one of the reasons I really sing the praises of the arctangent function is because of the rational functions. It shows up. It's a useful integral. It's not just a silly like, oh, ha, 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 he likes to say arctangent. It's a powerful thing. We use it. We use it. All right. So that's what you need to do first if your degree on the top is larger than the degree on the bottom. But that's not where we end. Because now we have a second step. So long division first if you need it. The second step is partial fractions. All right. Now, so there's a lot of words here, so I just don't want you to be too caught up on the words. It refers to what we talked about before. Every polynomial can be factored into pieces. And your pieces have two different types of shapes. One way it might look is like x minus a number. These are called the linear terms. Linear because linear is oftentimes referred to as a first-degree polynomial. The other thing it might look like is something in the form x minus a quantity squared plus b squared. These are called irreducible quadratics. It says you can't factor any further. Now, I should put a word of warning. It's true that every polynomial can be factored. In practice, some polynomials are very hard to factor. And the history of factoring is a very curious and strange history indeed. The polynomials that you will encounter are ones which should be very straightforward. So there should be very few surprises. Now, the question is, what are we going to do? And the answer is, for every term in the denominator, what we're going to do is sort of break things up as a combination of terms. So, if I see in my denominator x minus a to the r, I'm going to have a series of terms involving x minus a to various powers. So I start with x minus a squared, all the way up to x minus a to the r. If I see a series of terms which are irreducible quadratics, x minus a squared plus b squared to the r, again, I'm going to have a series of terms. But now, when I should have pointed out up here, these a1s, a2s, ars, they're constant numbers. They're numbers. When we have irreducible quadratics, the upstairs are going to be linear functions. So b1 times x plus c1, and so forth and so on. Now, this will become more clear about what's happening in a second, but the point here is we're essentially taking our denominator and we're going to pull our expression into smaller parts. But in order to do this, you have to know the values of the upstairs pieces, the a's and the b's and the c's that we're introducing. They're not arbitrary. They're numbers to be determined. And so we have to figure out what they are. Now, there's a comment here which says, if you set your equation up, it should be the case that the total number of things that you have to figure out, your constants you don't know, has to be the same as the degree of your denominator. If it is not, you've made a mistake. So go back and check your work. So here we go. So the procedure for partial fractions. If we're at the point where we have the degree upstairs is less than the degree downstairs, which will happen after we do long division if we need it, then we're going to take the downstairs and we factor it. All right, so now we've had the downstairs is factored into terms. We take the form downstairs, and we say, all right, given that what I have downstairs, I'm going to rewrite it as combinations of things that look like this. This will become more clear as we do some examples in a few minutes. There's going to be some unknown coefficients, but I know that my function can be rewritten in this format. And now we go through and we solve for our coefficients. All right, so let's do an example to help us see what's going on. So find the partial fraction decomposition of 5x plus 4 divided by x cubed plus x squared minus 2x. The first thing we check is we compare degrees. Do we need to do long division here? No, we don't, because the degree upstairs, it's a first degree. The degree downstairs is a third degree. Long division, not needed. So that was our first step. We just check. Now we need to factor the downstairs. So we have to start thinking, all right, how can we factor something like x cubed plus x squared minus 2x? Well, what's something we can do to this? We can pull out an x. X is common. Now we become x squared plus x minus 2. Are we done? What else do we need? Does the x squared plus x minus 2 factor? Yes? Okay, what does it factor as? Okay, so yeah, x plus 2, x minus 1. So, we can rewrite our expression as 5x plus 4 divided by x times x plus 2 times x minus 1. All right. So now we have our rational function in a really good form. Now comes the next step, which is we're going to take this and we're going to pull it apart. So we have 5x plus 4 divided by x times x plus 2 times x minus 1. Now, for every term downstairs, I'm going to have something on the other side. So here I have an x, and that's just to the first power. So that says I'm going to have something over x, and I don't know what it is, so I'm going to write it as a. Now I come to my next term, x plus 2. Well, it's to the first power, so there's only going to be one piece over here, so it's x plus 2. And upstairs there's some unknown. I'll just work my way through the alphabet. I'll use b. And then for the last term, there's my x minus 1. And again, that's something I don't know, so I'll put c up there. So that's what's happening. So in particular, this is what we meant when we said for every term in the denominator, we introduce appropriate parts. So, for example, we saw an x to the 1, so there was going to be just a single, some unknown number over x. And we did that for each term. We introduced the right form. So partial fraction says that this can be done for some choice of a, b, and c. But we have to figure out what a, b, and c are. Now, the next thing it says, if you have a really good memory or you're good at taking notes, is it says, let's clear your denominators. All right. Because fractions are tough. So let's clear our denominators. Now, how do you clear your denominators? Well, what you do is you take your expression here, and you're going to multiply by just sort of the right expression so that there's nothing left downstairs. What's the right expression? This piece. So I'm going to multiply everything times x plus 2 times x minus 1. And when I say everything, both sides. So as long as I do it on both sides, life is good. All right. On the left-hand side, what will be left? 5x plus 4. So 5x plus 4, and that's why we choose this. On the right-hand side, in the first term, what will we end up with? The x's cancel, so we're going to have a times the other terms. So a times x plus 2 times x minus 1. In the next piece, the x plus 2's cancel. So b times x minus 1. And the last, the x minus 1's cancel. So c times x plus 2. All right, so now we have to figure out what is a, b, and c. And there are two approaches. I'm going to just mention both of them. Number one, this is the way I like to do it. Wait, no, this is not the way I like to do it. Number two is. Yeah. Number one is the way that books like to do it. It's annoying. All right, but we'll do it. Okay. Number one says two polynomials are the same if only if the coefficients are the same. All right, that seems true. So set the coefficients of both sides equal to each other and solve. So what does that mean? Well, that means you get to expand. So x plus 2 times x minus 1, that's x squared plus x minus 2. Here we get x squared minus x. And here we get x squared plus 2x. So there's an a plus b, and a plus c. So let's see. What's in front of our x squared? Well, there's an a b, and a c. So a plus b plus c, x squared. What's in front of x? Well, here you get an a times x, so there's an a. Here you get b times minus x, so there'll be a minus b. And here you get a c times 2, so that's 2c. And that's my x. What's a constant term? Well, you get a times minus 2, so that's minus 2a. B times, well, there's nothing, so nothing. And c, again, nothing, so minus 2a. So that is the expand group coefficients. All right, fair, fair. But what do we have? We have a polynomial on the left, a polynomial on the right. And what we need to do is compare coefficients. So let's look at the coefficients for x squared. On the left-hand side, what's the coefficient for x squared? It's 0, because there is no x squared. So whenever it's missing, it's like you have 0x squared plus something. So okay, so that says that we need a plus b plus c equals 0. All right, we'll make a little note here. A plus b plus c equals 0. How about a minus b plus 2c? Well, that's the coefficient for x. What's the coefficient for x over here? 5. So a minus b plus 2c should equal 5. All right, so that's 5. The minus 2a, that's the constant. What's the constant over on the other side? 4. Right there, that's our constant. So minus 2a has to equal 4. And now what we have is a series of 3 equations and 3 unknowns. So we start solving. Is there anything that's easy to solve for? Oh yeah, we channel our inner Canadian. Oh yeah, A. Oh, don't you know A? Yeah, A. It's, what is A? -2. All right. Now, if you update that, well look, I can replace now, because I know A, I can put -2 into there, -2 into there. If I move it across, that tells me that b plus c, because there's a -2, that becomes +2, and minus b plus 2c, what would that be equal to? So I put -2 there, move it across, we get 7. All right, so now we're down to 2 equations and 2 unknowns. How do we solve this? Well, you can do substitution, or you can do combinations. I like to do things like add and subtract equations if I can get cancellation. I notice that the b's are set up to cancel. If I add the 2 equations together, on the left-hand side, what would I end up with? 3c. On the right-hand side, what would I get? 9. So what does that say about c? c is equal to 3. Now that I know c equals 3, I can come into either equation, doesn't matter. For example, the first one, I could say that b plus 3 equals 2. What does that tell us about b? b is -1. So, updating. We can conclude that 5x plus 4 divided by x times x plus 2 times x minus 1 is equal to a, which is -2, over x, plus b, which is -1, so I'll write that as minus 1 over x plus 2, plus c, which is 3 over x minus 1. So, we've successfully pulled it apart. And that's what we want to do. We want to pull it apart. So while the left-hand side would be hard for us to figure out how to integrate, the right-hand side, each piece is not so bad. It would end up being a bunch of logs. That's okay. We can handle that. Now, that was option number 1. There is an option number 2. This is the one I like, and I strongly encourage you to use it. Now, it might not work 100% of the time, but boy, it works really well. So, the first idea, number 1, says, hey, look at your coefficients. The second one says, you know what? Pick some good points. You must choose. But choose wisely. For as a good choice will get you closer to the answer, a bad choice will take you further from it. Now, what's a good choice? A good choice is something where we get 0. 0 is a great ally. So, let's look at our expression. So come back right to here. So the 5x plus 4 equals all of that stuff. So we're not even going to expand. And we ask ourselves the question, let's see if there's a nice value for x. Some choice for x, which makes a lot of the pieces equal to 0. And when I say a lot of the pieces, the stuff with the unknown parts, a, b, and c. Is there any nice values for x that you see? What? -2? Okay. If you plug in x equals -2, let's plug it into both sides. What do you get here when you plug in -2? -6, because you get -10 plus 4. So that's -6 has to equal, when you plug -2 into the first piece, what do you get? You get 0, because of that x plus 2 goes away. When you plug it into the last piece, what do you get? 0, because that goes away. When you plug it into the middle piece, you get something. Okay. So you get -2 times -3. -2 times -3, also known as 6 times b. So by plugging in x equals -2, we come to the conclusion that -6 equals 6 times b. What does that tell us about b? -1. Is there another good choice for x? 1. All right. We plug in 1. On the left-hand side, what do we have? 9. On the right-hand side, the first term, 0 because of that x minus 1. The next term, 0 because of that x minus 1. The last term, 1 times 3. So that's 3 times c. So what does that tell us? C equals 3. All right. Any other good choices for x? 0. Okay, let's see what happens there. Plug in 0. On this side, what do you get? 4. Here, what do you get? Minus 2a, because 2 times minus 1. Here, we're plugging in 0, we get 0. Here, we plug in 0, we get 0. So we can come to the conclusion that a equals -2. You can check. These are the same values that we got before. A is -2, b is -1, c is equal to 3. On the other hand, you might also notice this felt easier. So, my suggestion is use this as much as you can. Now, it may not get you 100% there, but it'll get you a chunk of the way. And any chunk of the way is going to make it so there's less work for you to do going forward. All right, so that is how partial fractions work. And we probably have enough time to do one. No, we can probably do 1.5. Yes, of course. So let's go through and do some examples. Find the integral 2x cubed minus 4x squared minus x minus 3, all divided by x squared minus 2x minus 3. What's the first thing we need to do? Long division, right? Because check the powers. Don't jump into doing that pooling partial fraction stuff until you've checked your powers. Okay, so we start with our long division. All right, so we're going to take our x squared minus 2x minus 3, that's our denominator, and we're dividing it into our numerator. Now, upstairs, there's actually no terms missing, so there's no need for a 0 placeholder. That's okay. X squared, what do I need to multiply to get to 2x cubed? 2x. So I'm going to multiply 2x now by that expression. So that's going to give me 2x cubed minus 4x squared minus 6x. Subtract. 2x cubes cancel. The 4x squareds cancel. That's coincidence. They normally wouldn't. What's left? Well, we have minus x minus minus 6x. So that would be 5x, because this is going to become a plus 6x, minus 3. And now, the power x squared is bigger than that, which means we stop. So this 5x minus 3 is our remainder. So that says that this is equal to the integral of 2x plus the remainder, 5x minus 3, over x squared minus 2x minus 3. All right, the 2x, that won't bother us, so we've got to focus our energy on this last piece. Now, what's our next step? Factoring. So after doing log division, factor. Now, occasionally, they'll have it factored for you. If they don't, that means it's got to be pretty easy to factor. All right, does x squared minus 2x minus 3 factor nicely? Yes. Oh, wow, they're just like, I didn't even check. I just know it's going to. Okay. What does it factor as? So I need two numbers that multiply together to negative 3, add together to negative 2. X minus 3, x plus 1. All right. Now we're going to pause our integration for a second and do some work on the side. So the work on the side is the algebra. And that algebra is what we're calling our partial fractions. So now for our side work. So we want to take 5x minus 3 over x minus 3 times x plus 1. And we're going to write it as something over x minus 3, so I've taken my x minus 3 part, plus something over x plus 1. All right, so that says partial fractions. We can rewrite it in that way. So this is sometimes the hardest step, is just getting into the habit of what's the right form. So it's good to just practice. Write down some polynomials, already factor and see, let me make sure I have this right. We're going to do several more examples. So we'll get some more practice. Okay, so that's the form partial fractions takes. What comes next? Yeah, multiply, clear out your denominators. Fractions are scary, so we don't want them. So we multiply by our original function here on the left-hand side, x minus 3 times x plus 1. So if we do that, we're going to just have the numerator on the left-hand side, 5x minus 3, is equal to a times x plus 1 plus b times x minus 3. Now you come to the part of solving for your constants. Here there are, like I said, at least two roads you can take. There's lots of ways to figure this out. Use whichever way you want. I personally try to do things which are simple, so I want to do it by choosing good values for x. Do you see a good value for x? Negative 1. So we plug in x equals negative 1. On the left-hand side, what do you have? We'll get negative 5 minus 3, negative 8, equals the first term. What does that do? Zeroes out. That means we chose well. The second term, what happens? We'll get negative 4, because minus 1 minus 3 is negative 4 times b. What does that tell us about b? B equals 2. Is there another good choice for x? 3. Oh, yeah. Okay, so we plug in 3. 5 times 3 minus 3, what does that become? 12. 3 plus 1 times a? 4a. 3 minus 3 times b? 0. That's why we know it's a good choice, because we got things to cancel. So, 4 times a equals 12. What is a? 3. So, now we are ready to resume our integral. So we've done our side work partial fractions. We now know that 5x minus 3 over x minus 3 times x plus 1, this says I can replace the b by 2. So this b can become 2. A becomes 3. So I can replace this by 3. So we get the integral of 2x plus 3 divided by x minus 3 plus 2 divided by x plus 1 dx. Now we go through and we write down our answer. Integral of 2x, x squared. Integral of 3 divided by x minus 3, It's definitely a 3. 1 over x. If you just saw 1 over x, what would it be? ln of x. If you see 1 over x minus 3, what is it? Natural log of x minus 3. 2 over x plus 1. 2 log x plus 1. In general, if you're integrating 1 over x plus a number or 1 over x minus a number, it's the natural log of x, whatever, plus that number or x minus that number. Okay, are we done? Plus c, because we're not going to miss that point. Yes, we might miss the other points, but not that one. We're going to get that one. That's a for sure. That's a for sure. All right. So, let's... Any questions on this one? Are we good? All right. Let's try this one. I think this one will be good for us to sort of remember what to do. Find the integral 4 minus 2y divided by y squared plus 1 times y minus 1 quantity squared. And I see a typo here. It's supposed to be dy. There we go. All right. Now you're like, oh, Steve, that was too easy. Just whatever that is times x. All right. Okay. dy. All right. Now, do we need to do long division? Yeah. Now, here you got to be careful and check. You check the degrees. Upstairs, what's the degree? 1. Downstairs, what's the degree? 4. Yeah, because the degree is if you multiplied it all out. Now, I'm going to come back to the degree and point something out in just a few minutes. So remember that number 4. It's probably not hard to remember. All right. So we don't need to do long division. Do we need to do any factoring? No. They factored for us. That was very nice of them. So we're ready to go straight into partial fractions. So we're not even going to start the integral. We're going to do algebra on the side first. So here we go. We're going to say 4 minus 2y, divide that by y squared plus 1 times y minus 1 quantity squared. All right. So that's going to be equal to something. Now, this one, if we go all the way back to a few slides ago, there's a couple of things we have to point out. Let's start with the y squared plus 1. Now, y squared plus 1, that's what we call an irreducible quadratic, which means you can't factor it any further. So when you have an irreducible quadratic, when you write it down, your upstairs isn't just a number. It's a linear function. So for the first term, it's going to be y squared plus 1 downstairs, and upstairs will be a times y plus b. All right. So if you have an irreducible quadratic, you have a little bit extra upstairs. But we can handle that. Now the next term. Y minus 1 quantity squared. Okay. So notice, this is a little bit different, because before we've only dealt with to the first power. Now it's to the second power. What does that mean? It means there's going to be 2 terms. So you have to have one for every power. So what are we going to end up with? We're going to have the first power of y minus 1, and then the second power of y minus 1. So y minus 1 squared. So you start with every power up until whatever power you have here. So we have to the first and then to the second. If this had been a cubed, we'd have another term for the cube. Okay, so that's the partial fraction decomposition. Now I said remember that number 4. Why did I say that? How many things do we need to solve for? There's 4 things to solve for. So that is the clue to sort of do a check. If the number of things you need to solve for is equal to the degree, that's a good sign you may have done it right. If they're not equal, that's a definite sign you did it wrong. So be careful. All right. Well, now what? Clear your denominators. Okay, so we're going to multiply everything, both sides, by y squared plus 1 times y minus 1 squared. On the left-hand side, we're going to get 4 minus 2y. Over here we get ay plus b times y minus 1 quantity squared, because the y squared plus 1's cancel. The next term, we're going to get c, and we're going to get the y squared plus 1, and we're going to get a single y minus 1. So c times y squared plus 1 times y minus 1. Then the last term, the y minus 1 squareds cancel, so we get d times y squared plus 1. All right. Are there any good choices to make? Y equals 1 is a good choice. What happens when you plug in y equals 1? Well, over here we get 2, 4 minus 2. The first part, what happens? Goes to 0 because of the y minus 1. The second part, what happens? Goes to 0, the y minus 1. The third part, what happens? 2d. Coming to you in beautiful 2d. All right, 2 equals 2d. What does that tell us about d? D equals 1. Now, it's a little bit less clear what to do next. Okay, so there are some things you could do, which is start doing imaginary numbers, but we won't do that. Like I said, there are limitations to how far you can get, but use as much as you can. You could, of course, keep plugging in numbers, but you won't get down to a single variable. You will get down to a relationship of variables, which may or may not be helpful. So what can we do here? Well, what I would do here is now say, well, okay, I've sort of maxed out as far as I can go with my various things. So there's two things, I guess. There's two options. Keep plugging in numbers. We won't get down to one variable, but we'll get simple equations. Or expand polynomials. And as much as I'm not a fan of expanding polynomials, sometimes you got to do it. So let's try that out. All right, a times y plus b. Y minus 1 squared is y squared minus 2y plus 1. Then you get c. And here we can actually just go ahead and multiply this through. Y squared times y is y cubed. Y squared times minus 1 is minus y squared. Then 1 times y is plus y. And 1 times minus 1 is minus 1. D times y squared plus 1. So what do we end up with? Well, we have a times, did I make a mistake? Or I think I'm okay. I'm going to multiply the y through, so y cubed minus 2y squared plus y plus b times y squared minus 2y plus 1 plus c times y cubed minus y squared plus y minus 1. Oops, forgot my parenthesis. And then, actually, we know what d is. We can just replace what d is. So plus y squared plus 1. Okay? And now we just group by coefficients. So the y cubed coefficient. Well, what's the y cubed over here? 0. So we get 0 equals, over here, well, there's an a, that's attached to a y cubed. Then no y cubed on that term. There's a c, that's attached to a y cubed, and there's no y cubed there. So we end up with the conclusion that a plus c has to equal 0. All right, well, that's useful information. We might be able to get something out of that. How about y squared? Well, there's no y squared, so we get 0. Over here, we have minus 2a. Here we have plus b. Here we get minus c. And then we get a plus 1. because there's a y squared there. How about for y? Negative 2 is equal to a, because there's a y times a, minus 2b. Then we have c times y, so that's a plus c, and then there's nothing else there. Now let's pause for a second. What do you notice about this one? I see a plus c. What do I know about a plus c? I know a plus c equals 0. Oh, this is cool. So that means I can cancel that, I can cancel that. What do we know now about b? It says b is 1. Cool, cool. Okay, let's go ahead and do our constant terms. I'll call it y to the 0, our constant terms. So over here, we get 4. We don't need to do our constant terms, but you know, you never know which ones are going to be the easiest ones to work with. 4, no constant term there. Here, we get our b, because there's b times 1. Then we get our minus c, because there's a minus c there. And then we get our plus 1. But we know about b, right? b is 1. So that says that for b plus 1, that would be 2 minus c. Because I can, b equals 1. 1 plus 1 is 2. What does that tell us about c? c is negative 2. Okay, c is negative 2. Come back to the first equation. What is a? a is 2. Okay, so there's a, b, c, d. So now we know what our constants are. All right, so we're almost ready to do calculus again. So it says this integral is equal to a times y, so that's 2y, plus b plus 1 over y squared plus 1, plus c, that's minus 2 over y minus 1, plus d, which is plus 1 over y minus 1 squared, dy. So partial fractions has allowed us to pull it apart. Now we can, of course, pull apart some more. This y squared plus 1, we saw this at the beginning of today. We could write it as 2y over y squared plus 1, plus 1 over y squared plus 1, minus 2 over y minus 1. What's a better way to write 1 over y minus 1 squared? Well, it's y minus 1 to the negative 2. So now we integrate, and in the interest of time, I'll just say the first term is log of y squared plus 1. The second term is arctangent of y. The third term is a log, 2 log y minus 1. The last term, what would that be? The integral of y minus 1 to the negative 2 power. So if it's just the y to the negative 2 power, the rule is add 1 to the exponent, divide by the new exponent. Does the minus 1 do anything? No, it doesn't. It's simple substitution. So it's the same rule. So it will become y minus 1 to the negative 1 power. Then you divide by negative 1, which makes this a subtraction. And then we want our points, so we put plus c. And that is the integral. That's not so bad. Well, maybe, but it's practice. And the more you practice, the better you get. So let's do some more examples. Find the following: the integral of t squared plus 1 over t minus 1 times t minus 2 times t minus 3. So we run through our procedure. The degree downstairs, if you multiply these all out, will be a t cubed. Upstairs we have t squared, which means we don't need long division. We already have a higher power in the denominator. So let's do our work to the side. And that is, let's do our partial fractions decomposition. So we have t squared plus 1. And the nice thing here is, this is a little bit simpler. It's good to go back. You know, we did a hard one. We need to start doing some cool downs. So t squared plus 1 over t minus 1 times t minus 2 times t minus 3. Each one of these is a linear term, so that's going to be able to handle. And remember, each one of these is to the first power. So what does that mean? Well, we're going to have something over t minus 1 plus something over t minus 2 plus something over t minus 3. And the exponent, sorry, the numerators are just some unknown quantities a, b, c. So now we need to solve for a, b, and c. So we clear our denominators. T squared plus 1 is equal to a. And so we're multiplying, remember, by t minus 1 times t minus 2 times t minus 3. So when I multiply here, the t minus 1s will cancel. So it would be t minus 2 times t minus 3 plus b. Now the t minus 2's cancel. So I'm left with t minus 1 times t minus 3. And lastly, the t minus 3's cancel. And so that'll become plus c times t minus 1 times t minus 2. All right. So what do we get? Well, let's always try to choose some nice values. And in particular, essentially if you go back here, the nice values are what makes 0 in your denominator. So we see 1, 2, 3. All right. So we say, all right, let's try 1, 2, 3. T equals 1. We'll get 1 plus 1, which is 2. Here we'll get a, so we're going to take 1 minus 2, so that would be negative 1. And 1 minus 3 would be negative 2, so 2 equals minus 2a. All right, well that says a had better be equal to negative 1. Good. Except I screwed up. Be careful, double check, right? 1 minus 2 is negative 1. 1 minus 3 is negative 2. So it's actually plus 2a, so a equals 1. Yeah, always double check your work. You know, as the saying goes, double check twice, you know, and then you don't have to fail. That's not really a saying, but it should be. It's really good advice. You know, small mistakes lead to big disasters. All right, next one is t equals 2. Because t equals 2 is going to knock out the a and the c term. Over on this side, we're going to get 2 squared plus 1, which is 5. And here we're going to get what? Well, we're going to get 2 minus 1, which is plus 1 this time. 2 minus 3, which is minus 1. So this will be a minus b, because they both have different signs. So we get that b should be negative 5. And t equals 3. These first two terms are going to knock out because of the t equals 3. We'll cancel the t minus 3. Over here we get 9 plus 1, which is 10. Over here we're going to get 3 minus 1, which is plus 2. 3 minus 2, which is plus 1. So we're going to get 2 times 1, so we get 2c. So that tells us that c should be 5. So, coming back here, we're ready to do the integral. Because now we have our way to pull it apart. So this says that we can write this as the integral of, all right, a, well, let's just update here. This is plus 1, b is minus 5, and then c is plus 5. So I don't remember which coefficient goes with which piece. So 1 over t minus 1 minus 5 over t minus 2 plus 5 over t minus 3, and that is dt. So we now can integrate each piece. Each one of these will be a log piece. So we get log of t minus 1 minus 5 log of t minus 2 plus 5 log of t minus 3. And because we want credit, plus c. Now I will comment that the integrals we've worked on today are all indefinite integrals. There's nothing here that says this doesn't work for definite integrals. We're just doing the practice right now. So if this had been a definite integral, then we would evaluate and we would be fine. Of course, one of the things you have to be careful of, since we're working with definite integrals, is what happens if we have zeros downstairs. Things might get a little bit improper. Well, we'll figure out how to deal with that another day, right? Well, we got to save something. We still have some time left in the course. Okay, one more example. Find the following integral. E to the t, upstairs, divided by e to the 2t plus 3e to the t plus 2. Now, the first reaction when you look at this is to say, this is not rational. Because if you look at what's going on here, you don't have a polynomial on top and you don't have a polynomial on the bottom. And therefore, partial fractions need not apply. All right, true, true. In the form that it's currently in, it is not a rational function. But that doesn't mean that it might not someday be. Remember that when we're doing integrals, our goal is to rewrite our current integral. And it's possible that in the process of rewriting, something rational might occur. Now, looking at this, it's not so clear how to proceed. But here's sort of a cool fact. I learned this once when I was yet a young mathling. See this e to the 2t? It turns out, and this is totally true, that e to the 2t is the same as e to the t squared. Now, you might be saying, hey, isn't it also true that it's the same as e to the 2 to the power t? Yes, but don't distract me. It's e to the t squared. So why is that helpful? Well, really, I should think about like, wow, everything is really looking like e to the t. So our idea is let's make a substitution. Let's let u equal e to the t. Then what would du become? Well, it'd be e to the t dt. Ah, right there. So by making a substitution, we'll get the numerator will become, well, we'll write it as du, and downstairs will become e to the 2t is e to the t squared, or u squared. 3e to the t is 3u, and plus 2. Now, this is starting to look like partial fractions. It's a rational function. So the power upstairs is to the 0th power. So in other words, it's a constant. I'm not saying that that's a 0. It's the 0th power. That's the degree of a constant. Downstairs it's degree 2. Don't need to do long division. So the next thing is we're going to factor 1 over, and this hopefully should factor. In fact, it doesn't look like it's too bad. U plus 1, u plus 2, and I'll put our du there. So now we're ready to do a little bit of work on the side. That little bit of work, also known as partial fractions. So 1 over u plus 1 times 1 over u plus 2. As we said, we don't need to divide. We're going to have our form, and this is part of the practice. You got to practice the form. Once you get the form down, the rest of it, it's not so bad. Just a little bit of work. So once it's the form, practice the form. Clear your denominators. Multiply both sides by u plus 1 times u plus 2. Then 1 equals a times u plus 2 plus b times u plus 1. Now it's not so hard to solve for coefficients, but I'm just so enamored with this idea of choose wisely. I'm going to keep going. If we choose u equals negative 1, what will happen? Well, on the left-hand side, we'll end up with positive 1. On the right-hand side, the second term goes away, and the first term will become a times 1. So we get that a equals 1. If we choose u equal negative 2, then on the left-hand side, we have 1. Well, because we always have 1. Now the first term goes away. We're going to get b times negative 2 plus 1, which is negative b, which really tells us that b equals minus 1. Or updating, 1 over u plus 1 times u plus 2 is equal to a over u plus 1, so 1 over u plus 1. Then plus b, which is a minus 1, so we can write it as minus 1 over u plus 2. So this is, again, this is algebra. This isn't calculus, this is algebra. Algebra is allowing us to pull it apart. So it's like, well, I don't know how to integrate that, but I do know how to integrate this. So we're pulling things apart. And by pulling it apart, by simplifying it, we've got a better chance of being able to integrate it. So, catching back up, we resume our calculus. So we rewrite what we have, 1 over u plus 1 minus 1 over u plus 2 du. And these are relatively easy integrals. So that's the natural log of u plus 1 minus the natural log of u plus 2 plus some constant c, which we don't know, but that's all right. And we're not done because we started in terms of t, so we got to end in terms of t. So this will be natural log of, replace u by e to the t. e to the t plus 1 minus the natural log of e to the t plus 2 and plus c. Now, you can, if you have logs, manipulate them. And keep in mind that anytime your answer involves a log, there's log manipulation tools. So it's okay if you write your answer in a slightly different way. For instance, I could have, if I wanted to, say, look, whenever I have subtraction, that's division. So e to the t plus 1 over e to the t plus 2 plus c. And that looks pretty good. That looks pretty good. There's other things you maybe could do, but I think that's about as good as we can do for now. All right. So this past lecture, this lecture, in both of them we saw how do we handle things. See, what didn't we do? Let's point out what we didn't do. When we had this integral here, we did not do bad algebra. So what's bad algebra? So if I had said, oh, look, hey, let me break it up as e to the t over e to the 2t plus e to the t over 3e to the t plus e to the t over 2. You'd never would have gone that, because this is bad algebra. This should never be done. Be careful. Don't do bad algebra. So instead we said, all right, look, we have these pluses in the denominator. What we want to do is somehow pull it apart, just like we do in the numerator. Pull things apart. And that's what's happening when we're doing our partial fractions. And the result is not so bad. It takes practice. It's not trivial, but it's not an impossible thing. It's practice. Work on the form. Know how to break it apart. And once you have that, just be careful, be methodical, and you'll be all right. All right, well, that's good for now. And come back next time when we'll delve into a different topic. And I believe next time we'll get to do numerical integration. Should be pretty good. Have a good day. Bye.